Great. Okay. Well, welcome everybody to our October AGU Geodesy section early career webinar. We're very pleased today to have Catherine Paterna with us today. Just as a brief introduction, Catherine received her undergraduate degree from the Massachusetts Institute of Technology, where she worked with Tom Herring, and it's great to see Tom's on the call today. We also got a PhD at the University of California, Berkeley, and has been at the USGS since 2019, and we'll be talking today about her research on shallow creep events from high-resolution space geodetic observations. So just as a note of as a formality for logistics, we will have everyone muted and turn off the chat during the presentation, and then at the end we'll open it up, so please have some questions ready. So without further ado, Catherine, please go ahead.
All right. Thank you for the introduction and for the invitation, Matt. And I'm happy today to share with you guys our recent research on the shallow creep events of the Superstition Hills and Imperial Faults. The presentation today will go into some what I think are exciting observations and delve a little bit into the implications, but I hope it generates some questions. So to start out, I will show some examples of the process of fault creep and how it affects the built environment in California. So here are some examples that may be familiar to those in the audience. On the left is the stadium at UC Berkeley, built on the creeping Hayward Fault. And on the right are two examples of fault crossing infrastructure on the Imperial Fault in California. And we can see right lateral offsets on each of these as they're part of the Pacific North American plate boundary, and we can see the impacts that it has on the structures. All of these faults creep, and in this presentation, I'm going to use some new observations from this past year to start to probe the question, how does creep occur? So the introduction, the outline of the talk involves an introduction where we'll discuss the key concepts of fault slip and describe the methods that I use. Then we'll discuss two specific creep events, both of which propagated from one place on the fault to another. One of them is on the Superstition Hills Fault, and the other is on the Imperial Fault. And then in the discussion, I'll describe some of the future implications, I think, and the kinds of studies that are set up by this work. So to introduce the concept of fault creep, first I'll start with a typical picture of interseismic deformation on a strike-slip fault. So our understanding of the typical strike-slip fault includes some combination of these features. Not all faults have all of these features, but often strike-slip faults have a seismogenic zone at intermediate depths in the Earth's crust that between earthquakes remains highly coupled and does not move, but can rupture in seismic events. Outside of that highly coupled region, sometimes we understand that there are shallow parts of the fault that can creep, and creep refers to the displacement along the fault that is slow, imperceptible, usually not seismic movement. So shallow parts of the fault may creep, deeper parts of the fault, which is thermally controlled, may creep, and then there's an intermediate zone that is probably seismically coupled on many faults. And this matches with our understanding of the mechanical properties of many rocks, which at depths and pressures associated with the seismogenic zone are unstable to frictional sliding, meaning they can rupture in seismic events. So we sometimes see slow, steady aseismic creep in the frictionally stable regions of faults, such as the lower crust and in the shallowest part of the fault, and the lock region slip in earthquakes rather than creep. An important thing to know about locked regions on strike-slip faults is that they can be modeled as elastic dislocations, and this style of deformation results in an arctangent shape in the measurements that we make of displacement or velocity at the surface. So the theory for this was laid out quite a while ago, and the arctangent function, which depends on the slip rate and the locking depth, was hypothesized for displacement patterns across locked strike-slip faults. And then for many decades, geodetic measurements from GNSS and INSAR and trilateration surveys have largely supported this model, borne this out, and we see this arctangent shape very, very commonly across strike-slip faults around the world. Now, of course, the picture that I've just presented is simplified compared to the real world, and in several ways, the real world can, in fact, be more complicated or even be the exact opposite of what I just described. So in this initial picture of a strike-slip fault, sometimes we see certain strike-slip faults that actually episodically experience the opposite of what I just described. And that's what we're going to look at in today's talk, is a fault where, on occasion, there are regions in the intermediate part of the crust that are actually capable of aseismic slip, while other parts of the fault may episodically not participate in those slip episodes. And then, as I mentioned, creep can be steady, but in reality, initially we think of creep as a steady process, and some faults do participate in steady creep, but other faults display episodic creep. So contrary to my initial picture, creep can be shallow or deep or intermediate, and creep can be steady or episodic. And so in this talk, I'm going to be investigating a fault or two faults that have episodic creep at intermediate depths. So importantly, we need to understand how to measure creep, and there are several different ways that we do this. So in this work, I'm going to use 3 different techniques to measure creep, and mostly they're familiar to folks in geodesy, but I wanted to just briefly touch on them so that we're all familiar with all 3 of them. Of course, we start with the GNSS technique, which involves an antenna attached to a deep drilled monument, measuring the position of a point on the Earth's surface very precisely. Here in schematic form, and then in real life, this station P503 is next to the Superstition Hills Fault, and this is the station that I'll use most of the data from in this talk. And of course, a GNSS station like this can produce a time series in vertical north, east, north, and up. And this time series, will look something like this, and we'll use that as the data for today's talk. The second technique that comes to play a lot in today's talk is INSAR, of course, interferometric synthetic aperture radar. And this technique uses the repeat pass of an active imaging radar satellite that sends a pulse of radar energy down to the ground and collects the reflected return. When the satellite repeats on the same orbit at a later time and performs the same process, the 2 images can then be differenced in their return phase, and the phase difference can be related to the ground deformation that occurred between the 2 passes. So the data looks something like this. And importantly, for this presentation, the satellite I'll be using is called Sentinel-1, and it repeats on its orbit every 12 days and images the ground with a radar at 5.6 centimeter wavelength. And then the third technique that I will use is from a creep meter. And this is a ground-based geodetic technique that essentially depends on a wire installed with an aperture of several meters across a creeping fault. And it's installed at an angle to the fault. And the creep meter, when the fault is displaced, the creep meter either extends or contracts, and the amount of extension or contraction can be related to the fault motion. The wire is held in tension, and it is kind of wrapped around these spools. And then the data that is collected from this instrument can look something like this. We have a time series of fault of slip or position of this wire, and it can be very, very precise. So as a table of all of these things, a summary, we have the GNSS technique, which provides high sampling in time, and the creep meter also high sampling in time every minute for the creep meter. Where an INSAR is lower temporal coverage, but it's higher spatial coverage, of course, because it's an imaging technique. And the creep meter has can measure even at the tens or hundreds of microns level. So each of these techniques, they have their strengths and their weaknesses. Some are point measurements, some are imaging measurements, some are high resolution in either space or time. But together, their complementary strengths and weaknesses can be used to provide a comprehensive picture of ground deformation. In this presentation and in the work that we're doing, I use all three of them. So on the topic of fault creep in California, it's important to know as a bit of background where creep occurs. Many of the strike slip faults in California have been observed to be creeping faults, and a number of them, as nicely summarized in this paper by Wei et al. 2013, are creeping in a sort of steady fashion, and then several of them are creeping in episodes. One of the places where fault creep is observed episodically is down here in the Salton Sea, and you can see there's many faults that creep episodically. So we're focusing on two faults here that I'll get into in just a moment. So the study region is called the Imperial Valley, and alternately known as, this region is known as the Salton Trough. So it's located at the southern terminus of the San Andreas Fault System. It's an transtensional basin. Connected with the extension across this region, there's high heat flow and geothermal resources here. The region is seismically active, often producing swarms of earthquakes and moderate sized earthquakes as well. So it's one of the more seismically active parts of California. The important faults to know about in the deformation field in this region are the San Andreas Fault here, which ends. The Superstition Hills Fault is this one, connected to some other conjugate faults. And the Imperial Fault is this one here that crosses the border between California into Mexico. The region is characterized by these dominant strike slip faults, but as I mentioned, it also has a number of smaller conjugate faults that are left lateral strike slip faults at perpendicular orientations, and it also has some normal faults in the region. Generally speaking, the geology of this region, it's a deep sedimentary basin, and it includes former lake sediments from when the Salton Sea in the geologic past was a much larger lake. The two important faults that come to bear in the observations from this past year are the Superstition Hills Fault, this one, and the Imperial Fault. Important background or context about these faults includes that the Superstition Hills Fault produced two magnitude 6 earthquakes in 1987, one actually on a conjugate structure and one on the fault itself. And then for the next more than 2 decades, actually for a very long time, the Superstition Hills Fault produced a major afterslip signal. The slip rate assigned to the Superstition Hills Fault in USURF3 is between 2 and 6 millimeters per year. And then we have the Imperial Fault down here, which produced several large earthquakes in the historic record, including a magnitude 7 earthquake in 1940 and a magnitude 6.5 earthquake in 1979. So this is a pretty major part of the plate boundary. It's assigned in the USURF3 fault model to be between 15 and 40 millimeters per year, but with the preferred value somewhere around 30. So this is thought to be a major player in the plate boundary. Both of these faults experience creep events frequently. And some of them, an important thing to know about some creep events is that some of them are triggered by regional earthquakes and some of them are spontaneous. So I'm not going to go into every single creep event that has happened on each of these faults, but there is a well-recorded history of triggered and spontaneous slow slip events or creep events on both of these faults. In the case of the Superstition Hills Fault, this symbol here on an early map, this is the creep meter. So the history of slip at that creep meter looks something like this, has a lot of after slip from the 1987 earthquakes, and some of these episodes are triggered. And then in the case of the Imperial Fault, there's also a history of creep. This creep meter here, labeled Ross Road, is the one that we'll use in looking at the data today. So armed with that context, we're able to go to the Imperial Valley this year and take a look at what took place in the spring and see how it fits into the broader context. Now, I'll also note that the reason these events in the spring of 2023 are interesting is because compared to previous events, they may be the best resolved with the geodetic techniques that we have available to us right now. So as I mentioned, there will be two creep events in today's talk. The first is on the Superstition Hills Fault, and the second is on the Imperial Fault. So we can jump into the data set for the Superstition Hills Fault creep event. The event was first observed or noticed somewhere around the 17th of May this past year, when the creep meter recorded a very large and sudden episode of creep. And you can see that it's also subdivided into eight or nine sub-events as well. For a bit of geographic context, the creep meter is located somewhere on the southern part of the Superstition Hills Fault, and the whole fault is 20 to 25 kilometers long. So the creep meter is here, and initially around the 17th of May, it shows a pretty large creep event. Relative to other creep events that have been seen at this creep meter before, this is one of the larger ones. So shortly thereafter, we were also able to look at the time series from this GNSS station. This station is, as I mentioned, P503. We saw the picture. It's installed about 280 meters east of the active trace of the Superstition Hills Fault. And so its position is able to record creep events. And this is a consistent story. Somewhere around the 17th of May, we also see this displacement in the time series. So these two are showing something consistent. Now, you may wonder what this looks like. These are some photos from Yuri Fialko that show field reconnaissance of this creep event. Somewhere taken the weekend after that the creep meter sent its time series. So this is the part that I found really, really interesting and surprising. So here we're turning to the INSAR data, and for me, this, as I mentioned, this was a bit of a surprise. The second image here, this shows a lot of creep. There's this localized displacement along the fault. This is a very clear creep signature. And this makes sense because this image spans May 15th to May 27th. And as I mentioned, on the 17th, we have the creep meter seeing displacement as well. So this is also a consistent picture where we see a lot of creep on the fault somewhere during this time interval. That makes a lot of sense because the creep meter agrees. Now, the part that's a bit of a surprise is that the interferogram immediately prior to this main one also is showing a creep signature. So right here, this is creep. And this interferogram tells us that the creep initiated somewhere between the 3rd and the 15th of May. And that is before we even knew it was happening, because we were not aware that the creep meter, at this point, the creep meter had no displacement. So this is, to me, the new observation relative to other times we've observed creep on the Superstition Hills Fault, is that this time this propagation is very clear. And it implies that there was a point somewhere here in the north central part of the fault where the slip initiated, and then it propagated outward because it reached the creep meter at a later time. So this is exciting. The propagation velocity can be calculated, assuming, so I'm going to make the assumption, at least to start, we do not know when this creep took place between the 3rd and the 15th. The INSAR can't tell us that, but I'm assuming that this little pulse here is kind of early in its process. And I'm assuming that we're imaging it kind of right after it began, and that this is going to continue down the fault. So assuming that the creep pulse is here at the 15th, and it's here by the 17th, that propagation velocity is calculated out on average to be about 10 kilometers per day. I typed this into Wolfram Alpha to see its velocity in a number of different units, and it turns out that this is actually very close to the maximum speed of a sloth. We processed a number of other interferograms along this same track and found creep in a few other moments in time. About a month later, there's a smaller burst of creep on the northern end of the fault. And then a month after that, a little bit of creep at the southern end of the fault, and the creep meter observes this too. So they are internally consistent. And I'll show in a slide or two another view of how of the creep spanned by each interferogram, so you can see how this stacks up. It implies that it's a bit of a bursty process. And this, to me, I interpret these little episodes of creep at the ends of the fault to be kind of like an aseismic equivalent of an aftershock. And you can see on another plot why it kind of looks like that. So on the topic of propagation, which I think is something exciting that can be pulled out of this data set. We know that the GNSS station is located somewhere intermediate between the initiation point of the creep event and the creep meter. So the kinematic positioning results from Tom Herring and Mike Floyd processed in track of this station, P503, relative, the differential position relative to a nearby station, produced at a 15-second interval and then smoothed. They give us a sense of where when the creep reached the GNSS station. Now, this analysis is still very new and very ongoing, and there's various ways that we can look at the time series and identify when a transient initiated, but at a very preliminary stage, we can identify a couple of points in time, such as we know when the INSAR pass satellite acquisition took place. We know when the creep meter, certainly we know when the transient began here. And what it looks like from this preliminary analysis is that, as I mentioned, the overall propagation velocity is somewhere like 10 kilometers per day, but the velocity between the GNSS station and the creep meter is faster, much faster, at something like 42 kilometers per day. So this is interesting as well. It kind of suggests that this process is not propagating at the same speed everywhere. It's bursty in time, but it may also be bursty in space. Here's another way of visualizing all of the creep that took place on the fault. I've given a smaller version of the different interferograms. And so you can see in the first interferogram, this plot is made by analyzing profiles every 50 meters along the fault trace and finding the displacement between the two different sides of the fault. And on the first interferogram, the slip looks something like this. And on the second interferogram, this is also projected into horizontal, assuming no vertical motion and assuming fault parallel displacement. The strike of the fault changes. So we projected with a different strike, along each point on the fault. This is one way of visualizing both the outward propagation from the initiation point and visualizing these little aftershocks, as I mentioned, right here and right here, which took a month here and 1 month before this happened and 2 months before this happened. So clearly the full process of this creep event was fairly complicated and took some time to evolve. Here's another way of looking at the outward propagation that we can see from this data set. And this tells us something a little bit different in its own right. We can look at the we can look at extract individual profiles and visualize them. And so we can see in the first interferogram from May 3rd to May 15th, this is the initiation phase, somewhere around profile D. It's very clear there's an event happening. And then in the later period of time, it has propagated outward, both in the north direction and the south direction. And there's more that we can see from this plot as well. One thing we can tell is that the surface break is very clear down here in I and H, where I've put different colors, just so these profiles can be a little bit distinguished from one another. This is a clear surface break visible in the INSAR right away. However, the other profiles are not as clearly breaking the surface, and some of them, the rest of the profiles seem to be continuous, and this looks like an arctangent. So it's suggestive of a buried dislocation, and by modeling the width of the dislocation, we can estimate its locking depth. So for each of these profiles, we produced an arctangent shaped model, and we found that the locking depth is something like 15 meters. We can see here on each of the profiles, the best fitting arctangent function has locking depths somewhere between 15 and 40 meters. And this was a bit of a surprise. This is very shallow for something to be happening in a geophysical process, and suggests in one interpretation that the slip mostly stops in the upper few meters of the soils. But there's more than one interpretation. So I'll get into this for just a little bit. We have two thoughts for the reduction in slip in the upper meters of the crust. One is that 15 meters is an approximation, we think, based on a well nearby. The 15 meters is approximately the water table. And so for some reason that remains to be investigated further, it could be that that the fluid saturated rock is able to sustain creep events that propagate through it, whereas the material above the water table has different properties and does not deform in the same way. The second option is that the shear strains sustained in the material could have been high enough that the strain was not elastic at all, and instead was a distributed plastic or inelastic deformation. And these are both available interpretations. We're not quite sure which one. Neither of them really explain the fact that in the central south part of the fault, the material broke to the surface. But when it comes to observations of material properties that change in this range a few meters below the surface, this is not the only time this has been observed, kind of surprisingly. In the rupture of the 2014 Napa earthquake, measurements of vineyard rows across the fault from Brooks et al. 2017 actually show a similar arctangent shape with a similar locking depth, somewhere between 5 and 30 meters below the surface. So this process is not unique to our study, but it's still something that we are trying to interpret and explain. I want to add one thing as well about the Superstition Hills fault event, which is that this seems to be an event with very similar characteristics to a slip event on the Superstition Hills fault in 2006. So here on the left is a plot of the time series from the creep meter. It's the same creep meter. And the time axis, of course, is from 2006, but the 2023 event that I'm describing here has been superimposed on a shifted axis. And we can see how similar these two creep events appear in space, in time. It's likely they're also similar in space, but that work is the quantitative comparison between these two events is very interesting and still ongoing by some of the folks on this call. So that kind of summarizes the observations and a little bit of interpretation that we have for the 2023 Superstition Hills creep events. And then next, I want to bring our attention for a few minutes to a smaller creep event that took place about a month before in the Imperial Fault. This event shows similar characteristics. It's measured by 3 different geodetic techniques, and it propagates from the north to the south. So similar, but it's smaller in every way. So it's not as easy to analyze to fully get the dynamics, but it's important because we haven't seen propagation on the imperial fault very much before. So let's turn our attention to this fault, which is in the agricultural part of the Imperial Valley. It crosses a number of roads between agricultural fields, and as you can see, it kind of presents some challenges. I went through the imagery. This is from July, and this is from May of this year, but going further back in time, they've needed to add some patches to this road as the fault has experienced some creep. So let's characterize this event a little bit as well. This event, similar to Superstition Hills, was first identified on a creep meter, and this creep meter is somewhere in the south of the creeping section. It was identified as 8 millimeters of creep on about April 17th. So we did the same process. We went through the INSAR, we went through the GNSS data, and we found the following. We found an example. We found a creep event that began in the interferogram prior, just like the Superstition Hills fault. So the creep meter is somewhere down here in the south, and the creep event begins more than 12 days earlier in this northern part of the fault. And then proceeds, propagates southward, and reaches the creep meter. This data, you can tell immediately, this is not as clean as the Superstition Hills fault in the desert environment. There's a lot more decorrelation in the INSAR, but if you look at features that cross the fault, such as roads, it's clear that there is some creep. And then we looked at one GNSS station that's less than 1 kilometer from the fault, and we looked at the creep meter. So this is smaller in every way. As I mentioned, this displacement from the GNSS station is only about 2 millimeters, but it's there, and it also tells us that this creep event, it gives us some idea of the timing of the creep event and the magnitude. So this creep event was about 8 kilometers start to finish. It took something like 20 days, and assuming a slip amount and a locking depth, we get an estimated moment magnitude of something like a 3.6. Whereas the estimated moment magnitudes for this event here is something like a 4.7. So it's about a 1 magnitude unit smaller than the Superstition Hills fault. We can also draw profiles here and evaluate a locking depth, just as we did for the Superstition Hills fault. And in this case, it's actually much harder because there's fewer locations where we can draw clear profiles across the fault. But in those cases where we are able to see displacement, it looks kind of like the majority of the Superstition Hills fault, where it looks not exactly surface breaking, but getting close, and the locking depth is modeled somewhere around 12 meters. So what can we learn from these two events that happened in 2023 and were well recorded? Well, one of my first questions was to understand what we know about propagating creep events in the literature. Propagating creep events on strike-slip faults have been seen before, but not as clearly as what we're seeing right now in INSAR, where it's very obvious from one acquisition to the next that there's been a propagation. Previous studies of creep events kind of date back to the 1970s, where there were propagating creep events from several creep meters installed along strike. And here I'm showing several examples of those on the San Andreas fault, near its intersection with the Calaveras fault, and in one case here on the Imperial fault. In going through this literature, I was somewhat surprised at how similar some of the kinematics of these creep events are to the ones that we've seen in the Imperial fault. Some of them have similar lengths along strike, 6 kilometers or so, for the Calaveras fault, for example. And their estimates of the extent of creep here include about 2 kilometers deep, which has been cited for the, is similar to an estimate in Way et al. 2009 about the Superstition Hills Fault creep event. And here also we have an example of a modeled very shallow layer, estimated at about 50 meters, that did not slip. So a lot of these features that I'm able to analyze in the INSAR data are very well presented already from a couple of creep meters in the 1970s. So this was impressive, and it allowed us to understand some of the ranges of velocities that have been observed. For example, these creep events move along strike at velocities of, in some cases, 1 to 3 kilometers per day, and in other cases faster, more like 5 to 20 kilometers per day. A really nice compilation of along strike propagating creep events on strike slip faults was produced by Dan Gittins and Jessica Hawthorne in 2022. This study analyzed creep events along the San Andreas Fault with all of the available creep meters from 1985 to 2022. And there are very many creep events that propagate between one creep meter and the next. Their propagation velocities, as compiled here, are shown in this histogram. The velocities that we're seeing on the Superstition Hills Fault and the Imperial Fault kind of fall right here in the region of maximum probability from these histograms. But this is showing us that the velocities can vary, and I'm not sure it's totally well understood why, or what controls the propagation velocity of a creep event on a strike slip fault. So as we kind of broaden our perspective a little bit, many pieces of research have been performed on slow slip events in subduction zones, as well as slow slip events on strike slip faults. And for those of us who study subduction zones, the propagation velocity that we've obtained of 10 kilometers per day is sort of a provocative number, because here the process of slow slip in subduction zones, which is a different process occurring at about 30 to 35 kilometers deep in the subduction zone, and producing seismic tremor. This is a different process, yet it's been observed to propagate along strike at approximately 10 kilometers per day, in a whole range of studies and across many different subduction zones. So we're finding a propagation velocity in the shallowest part of the crust that's really very similar to what's been observed in subduction zones. And so this prompted us to ask, what can we learn from these shallow events that may relate to the subduction zone process? So a topic that's been debated a lot in the literature over the last 20 years has been the scaling between the moment of a slow slip event observed in the subduction zone usually, and the duration. And these are both observables, so it does make sense that we can learn something by relating one to the other. So the two creep events that I have analyzed in the data section of this presentation, they plot on this plot right around here. And this looks, at first glance, it looks like this breaks the scaling relationship, but it doesn't necessarily break the laws of physics in any way. A recent reanalysis of this data by Ide and Baroza in 2023 suggested kind of a new interpretation of the fact that many of the slow slip events and low frequency earthquakes and tremor sources, many of the family of slow earthquakes, they plot on this presumably linear line between moment and duration. And there's other interpretations, but the initial interpretation of this line is that all of the families of slow slip events would plot on this line, but the reinterpretation actually suggests that there's a whole region of this plot of events happening at a certain with a certain moment and happening over a certain period that are nearly impossible for us to detect due to the noise limitations of our instruments. So they call this, in Ide and Barossa 2023, they call this the hidden region. And they go through the expected noise characteristics of seismic and geodetic data over certain frequencies and posit that any slow slip events in subduction zones happening within this region they could happen, but they would be not observable due to the noise characteristics. And therefore, they reinterpret this linear scaling as a speed limit, an upper speed limit. So slower events can happen, but they would be not observable. So in this context, that seems to be what we're able to observe here, perhaps benefited by the fact that we are observing in the shallowest layers of the crust. We have a geodetic sensitivity to slow slip events that are taking place, but at a slower speed than what we've observed in the linear scaling relationship of Ide et al. 2007. One of the other findings that I've mentioned about our results so far is that the creep event, the velocity of the creep event, we know that it's intermittent in time, as we see here. Just the time series of the creep meter can tell us that. But the compilation of our various data sets also suggests that this process may be burst-like in space as well, because we have a different velocity for propagation, whether we look at the overall picture or whether we look at one little part of the fault, and a different and a very slow velocity for the imperial fault that we cannot determine whether it was a steady process or an intermittent process with a pause. This finding is consistent with recent work in subduction zones and strike slip events as well, that basically suggests the closer we look in terms of time resolution, or resolution in space or resolution in time, the closer we look at a slow slip process, the more kind of burst-like patterns that we see. So for example, a large slow slip event in a subduction zone, when we look much closer, can in fact be made of a series of smaller slow slip events that together create the larger one. And this is similar to a recent paper that investigated a Cascadia slow slip event from with GPS time series that were subdaily. So it seems to be the case that the closer we look, the more burst-like behavior we see in slow slip events. So in the last couple of minutes, I'm just going to touch on modeling implications without going into too much depth. There have been several proposed mechanisms for episodes of slow slip, because as I mentioned, the process of slow slip is easiest to explain as a slow and steady process, but is more difficult to explain when it's burst-like, but does not reach seismic speeds. So the two most commonly proposed mechanisms for modeling of slow slip events include, first of all, a combination of velocity strengthening and velocity weakening materials. These are layers of the crust that are stable to sliding and that are frictionally unstable. And if you combine velocity strengthening and velocity weakening layers of the right sizes in the right combination, you can create a crust that has a type of stability that can create slow slip events. Often these models are sort of one-dimensional, and to produce propagation, such as what we see in this study, propagation that is burst-like or intermittent in space and time, like this little inchworm, to create that realistic propagation, recent studies have added even more complexity to the system in order to get the slip events to propagate along strike. Another possible avenue for modeling for modeling slow slip events is to use fault zones that include dilatant strengthening and pore pressure diffusion. This has been invoked many times in in modeling studies of slow slip events. I'm not going to posit which ones of these are the best for explaining our particular observations. I think that is work that can follow more in the future. But what I'll say here is that the shallow slow slip events that we're seeing and we're resolving in time and space could be model systems to help us test these various hypotheses. And they could present data sets that we can model in the future. So I'll conclude with a couple of key points and leave with some open questions as well. So on the superstition hills and imperial faults, multiple geodetic methods are able to resolve propagating time-dependent slip events. On the superstition hills fault, especially, the imaging is really quite clear. Number two, the propagation velocity that we infer is intermittent, and it averages 10 kilometers a day for the Superstition Hills fault and 1 kilometer per day for the Imperial fault, but it could be more burst-like, going as high as 42 kilometers a day for segments of this fault. Number three, of course, slip events impact fault crossing infrastructure, and they impact our understanding of calculation and budgeting of moment magnitude on these faults. So they're important to understand. And then in this study, I'm presenting a few firsts, I think. This is one of the first times we're able to use a high rate GNSS station as a creep meter and compare it directly to a nearby creep meter. And then we're able to investigate creep event propagation directly with INSAR interferograms. For me, this was impressive that it was seen from subsequent interferograms. We didn't need to do a stacking or time series for this. It was a sort of a lucky coincidence here. And we're able to see the propagation of the creep event using 3 distinct measurement techniques. So lastly, there are a lot of open questions that lead to future research directions. One, of course, is can creep event detection become more automated? We only have creep events and creep meters in several places, and with INSAR imaging, we have the ability to see a lot more along the faults. There's likely to be more creep events in places that we haven't seen them on creep meters just because we haven't had them there. Of course, are the slip distributions of slow slip events consistent in time? This is an interesting question that I think is already being researched, but I'm curious to see these results. Why do only certain faults participate in shallow slip events? Does a slip event know how big it's going to become when it initiates? And of course, what factors control the propagation velocity of a slow slip event? I think these are not simple questions, but they are questions that we can get closer to with the high resolution types of observations that I've shown here, and hopefully the research will kind of proceed in these interesting directions on the basis of the observations that we have now. So with that, I thank you very much for your attention, and I'm happy to take your questions.
Great. Thank you so much, Catherine. That was such an interesting talk. So I'm opening up the chat, and people can now unmute themselves or raise their hands if they have any questions. So I don't see anyone at the moment. Someone has raised their hand. Let's see if I can find them. Okay. Ellis, feel free to unmute yourself.
Hello.
Hi.
Hey. Well, thanks for a very nice talk, Catherine. It's really cool to see how everything's come together. I was curious, I think, if I remember correctly, P503 is sort of located right where slip becomes much more localized at the surface, where we start to see like actual clear surface breakage in the INSAR data. And so I was curious if you like thought much about if there's any connection with that to the potentially much higher propagation velocity in that segment, because that seemed quite interesting that it was like 4 times higher along.
Yeah.
I mean, it could, if it's just sort of burst like, at any given phase, it's maybe hard to say, but I thought that was interesting that sort of along that segment where the slip is much higher in amplitude and also much more localized, that it's much faster, it seems.
Yeah, that's a really good point. I hadn't thought about that yet, but that seems to make some intuitive sense to me too, where here the fault has a lot of complexity and it has some releasing bends. There's been suggestion in the past that creep events that enter these releasing bends, if there's dilatancy and the effects of pore fluids in these releasing bends, they could cause the slip to be especially halting, to start and stop. And maybe it's the opposite here. That's a really interesting question.
Cool. Well, thank you.
Great, thanks, Ellis. Tom Herring, would you like to unmute yourself?
Yeah. Oops, thank you. Yeah, enable start video. Interesting. Yeah, very nice talk, Catherine. I'm just curious about the magnitudes. Your creep meters showing 35 millimeters of motion, and yet the GPS site really only moved by maybe somewhere between 5 to 8 millimeters. I'm just curious why that disparity in magnitude.
Yeah, I think we need to model this, but my hypothesis is that because it's about 300 meters away, that it could be sensitive to the slip that's several hundreds of meters deeper, and that the displacement grows as you get much closer to the fault. So it could be related to essentially the aperture, but modeling would answer this.
Okay, thank you.
Great, and we have a few questions in the chat. I don't know if you can open up your chat, Catherine.
Oh, questions. Great. Did you look at the relationship of the creep events you observed and the microseismicity nearby? We looked for some microseismicity just in the USGS catalog. We have not seen microseismicity nearby, but that doesn't mean it's not there. Oh, I don't have in the backup slides that exact one, but so far this process on the Superstition Hills Fault is not associated with microseismicity, but it could still be, just not cataloged. And Eric Fielding, thanks. For the Superstition Hills Fault, the first patch that slipped seemed to have less displacement in the second interferogram. Do you have an explanation for that? Was it vertical motion? We do not have the other Sentinel-1 look direction, because it seems to me that after the Sentinel-1 constellation just became Sentinel-1A, I do not think they're collecting ascending in this place. But it does here, yeah, this is a good image to show it. There seems to be less slip in the second interferogram. Yes, right here. My thought about this is that mostly the process is complete by the 15th in this place, and so it didn't need to slip any further. But it also, one interesting thing that I've also observed is that when I model the arctangent function here on the first image, it has a locking depth of about 50 meters, and then when I model the sum of them put together, it has a locking depth of about 40 meters. So there's a little bit of a displacement here, and it's possible that this is telling us that, at least in this initiation point, the slip started at depth and came up. Is there any evidence from Meredith? Hi, is there any evidence these crustal creep events are seasonal in nature given close location to agricultural areas? I am super interested in knowing more about this because I also observed, and this is likely coincidental. I'm not going to make any strong statements about this, but this is the Imperial Fault creep event from a paper in 1978, and it happened on the exact same days in April that the creep event happened this year in the Imperial Fault. So the creep meter in Ross Road we're seeing April 17th, and it was creeping from the end of March to the beginning of April. So I've noticed that it happened at the same time of year twice, but that's just, you know, a single observation. Yuning, I'm wondering about the timing. Oh, it's the same question. Maybe. Yes, the answer is maybe. And I would be interested in understanding that question more.
Great. Well, I think that's all the comments in the chat at the moment. People should feel free to add one or unmute themselves if they have a question. I had a question for you, Catherine. I don't know if you looked at I guess there's some episodic events maybe on the North Anatolian Fault as well. I don't remember a lot of details about that. How do those compare?
They have, right, there's a few places on the North Anatolian Fault where the creep meters, there's several creep meters installed in Turkey on the same fault, and they have a propagation between them. Their propagation velocity is faster than 10 kilometers per day, more like in the 40 kilometers per day range, I think. And then on the North Anatolian Fault, that's Baptiste Rousset has a paper about that. I don't recall if they've propagated there. I could be wrong, but what I remember about that paper is that they needed that to find the creep event required beating down the noise through stacking and time series analysis enough that if there was propagation, it might not be as well resolved. So it's kind of an open question, and they may well propagate, but maybe we don't see them as clearly as we do in this desert environment.
Also, I was curious about using a fiber optic cable. Is that an option of burying one next to these faults to try to see the propagation for the next event?
Oh, I have not thought about that, but that would be really, really interesting. Because this is the kind of speed that would be well captured along many of those channels. We could easily follow it along a cable. I think that's a neat idea.
All right. Any other questions?
Catherine, it's Tom Herring again. You've got data from the same creep meter from 1977, presumably up to now. What else does the rest of the record actually look like?
There are a lot of things in the record that are not creep events. And this is also partially a question for Roger Billum. There, most commonly when the fault is not creeping, the creep meter shows signals that reflect a lot of things based on temperature and rainfall. So the fault can sometimes dilate and it can respond to hydrological events. So sometimes it's been the case that interpreting what's inside of the creep meter record is not simple. But when the fault is creeping a lot, then it's an easy interpretation.
Okay, thank you.
Great. Well, we're about to the top of the hour here. I want to thank Catherine again. It was a fascinating talk. We are going to make the recording available, so it should be available for all your friends to view on YouTube, hopefully in the next couple of days. We will be taking a hiatus from the AGU Geodesy Early Career webinars for November and December as everyone prepares, or some people prepare at least, for AGU meeting that's coming up in San Francisco, and hopefully we'll get restarted again in January next year. So thanks everybody for joining, and thanks again to Catherine.
Thanks, Matt.